identity matrix. It's a Kronecker product. Oh, this one's awful. You can look at 2 by 2 2 by 2 quaternion matrices. That's that's 4 quaternions. Each one of them costs you 4 quaternions. Each quaternion costs you 4 real variables. So we're talking about 16-dimensional algebra here, non-commutative, quite awful. We've actually calculated equations in that thing. That was one of Bailou's jobs, was to calculate the A Laplacian in this thing. We used Maple to do it. I think the A Laplacian in that algebra was a couple pages. It's really awful. The number of Cauchy-Riemann equations in that algebra is 16 squared minus 16. Oh. And then another, this I don't use enough, I should use this more. The group algebra, we can take any finite group and make it into an algebra just by taking real linear combinations of the group elements and multiplying in the natural way. The hyperbolic numbers are the group algebra of the finite of the cyclic group of order 2. 3 hyperbolic numbers are the group algebra of C3. The 4 hyperbolic numbers are the group algebra of C4, right? Not every algebra is a group algebra, but many are. And that finally brings us to what I was planning to talk about today. But it's good, since I'm going over, we still have 10 minutes, right? Okay, thanks. Appreciate that. So we have this list of examples. Now I want to talk to you about a differentiability. Now, first things first, differentiability involves a limit. So I have to set up a limit. I'll try to be brief. Basically, the point is we can take a basis for the algebra, and we can just make a norm up which basically treats that basis as a Cartesian coordinate system. And if you define it as such, you can prove it's a norm and go from there. And that's my approach. So basically pick a basis and invent then a norm which makes that basis orthonormal, right? Like so. So the norm of this will be x, the sum of the squares of the components. And you can always do this for any algebra. So we always have a norm to work with. And one of the things you learn in topology or analysis somewhere is that it doesn't matter what your choice of norm is. The limits which you calculate are independent of the topology which you use on a finite dimensional normed linear space. So we're not creating any artificial things by making this ad hoc norm. If we chose a different one, it wouldn't change anything. So there's no danger in that. Oh yeah? That's good. Now here's I stated that there's a submultiplicative constant, right? And I told you it was the square root of 2 for the hyperbolic numbers. Here's the theorem. There exists this m sub a, which, the norm of the product is less than or equal to the product of the norms times this constant. Here's my proof. It relies on the structure constants I introduced last time. If we take C to be the max of all the structure constants, which for everything I've shown you so far is just 1. The big C is 1. I think pretty much. Almost every structure constant I've shown you is either 1 or 0 or minus 1 so far in all our examples, I think. Okay. Anyway, here it is. So that's the norm of x times y, which is this times this. But by linearity, we can write that as the sum over ijk. I convert the vi times vj times the cijk vk. That's definition of structure constants. Then I pull the sum over k out. That's the definition of the norm with respect to the basis. Notice the v's are gone now. Why is there still a... there's a typo here. Son of a gun. That is supposed to be a y. See? We accomplished something today. I need to fix that. Part of the reason we're doing this. Not the best reason, but it's a good reason. So obviously I need to make that a y. All right. as you can see, it became a y in the next step. What do you know? And so what's this step here? Well, this is the definition of the norm, sum of the squares. Right? Now each component is the sum over the structure constants, like that. Right? That's the kth component right there. And then what do? I say that this is less than or equal to, see what I did? I traded out my structure constant for the maximum value that it takes on. And I traded out these possibly negative components for the absolute values of the components. These are real values. So I can take the ordinary garden variety real and real, absolute value there. Then what did I do? I pulled the c out, became a c squared. What's this n about? Well, you notice that this has no k. So the sum k equals 1 to n is just n. That's where this n came from. Now I got this, but if you look at that, that's equal to the product of that and that, because again, the I and j are decoupled. It's just like when you have the integral of rectangular bounds of x times y. You can break it into integral of x times integral of y with separate bounds. Same thing, but finite sums. Anyway, that's a relatively obvious step. And then I break it into two pieces. What are these pieces here? Why did I do this? Sum over that. Oh, because you might notice that that has lots of cross terms, right? We're talking about like absolute value of x1 plus absolute value of x2, da-da-da, plus absolute value of xn. Take all of that and square it. So yeah, it's got the product of like absolute value of x1 squared and absolute value of x2 squared, but it's also got all of those cross terms, right? The cross terms I wrote over here. So here's the diagonal terms, here's the cross terms. And then what did I do? I just said, well, the basis that the norm that I construct, part of the reason that I constructed it as it did is a very important thing. Remember this from advanced calculus. We want a norm such that the length of a vector is what? It's always larger or equal to the length of any component of that vector. Working in a basis where that is not true is possible, but unpleasant. I like my basis to be pleasant. I've constructed it so that this is the case. So this is, each one of these is less than the norm of x. I get norm of x squared, right? So I've got, this is literally the norm of x squared, norm of y squared. And this right here, if you look at how many different ways are there for k not to be equal to L, where k and L are taken from n indices? N squared minus n ways, because it's everything except for the diagonal. Only on the diagonal in KL space do you have k equal to L. And so that's n squared minus n plus 1. And there you go. That's my m sub a right there. That's, well, the square root of that is m sub a. This derivation is for any algebra. I was happy when I found this. Nathan doubted it at the start. But by the end of it, he's like, wow, you could actually do that. I was like, yeah, it actually wasn't that bad. And this is actually, I don't know, you might be able to improve on it. If you actually sort out what this means for the hyperbolics, it's like hyperbolic numbers, right? Have n equal to what? 2? And so you got 2 times 4 minus 2 plus 1, which is what? 3. 2 times 3 is 6. C is 1. You look at it, the maximum structural constant is 1. So this is 6. So m sub a is the square root of 6 from my theorem. But this does not give you the best m sub a for an algebra. It gives you an m sub a which is true. It's not sharp. The square root of 6 is not sharp. You can sharpen it. If you study the hyperbolic numbers more carefully, you can discover square root of 2 is a better estimate. Now that's an open question for me. How do you discover what the best choice of m sub a is for a given algebra? I don't have a particularly elegant way to answer that in general. That's something that's kind of left there for me. I try to get students to do numerical probing, but I've had mixed results with students being successful in trying to figure out that. But, I mean, for example, I don't know what the m sub a is for H3. Off the top of my head, I don't know what it is. I know it exists. I know I could make it what the theorem says. I'm not sure what the optimal choice is. You gotta find some place where it's equal, right? And then if you find some place where it's equal, then I think you can't sharpen it from there or something. I don't know. There's
Can you say again what makes one number more optimal than the other?
square root of 2 is smaller than square root of 6.
So optimal almost always means it's the smallest possible.
Well, that's what I mean, the smallest possible m sub a.
Okay.
Such that if you tried to make it smaller, it would not be true for some points in the algebra. Yeah. All right, I talked entirely too long about that. So anyway, the point is we have a norm. We can define limits in the usual way, advanced calculus. And here's our definition of a differentiable. A function from some open set of the algebra to the algebra again is said to be a differentiable at a point if its differential is a right linear map, if it's in the regular representation of A. So what I'm saying is that a differentiable function is a real differentiable function with a differential which satisfies this additional algebraic condition. That's an equivalent way to write my definition. Okay? Now, to say that this is a right linear map is to suppose that you can pull the scalars out like that. And that also means, of course, then that the Jacobian matrix of the differential must be in the regular representation, the matrix regular representation. And when we look at that, that will mean that we have the Cauchy-Riemann equations for the different components of the function. That's where we're going. Here's a few. Let me skip ahead a bit. Oh, actually, no, I don't have many Cauchy-Riemann equations in this. The place to find a slew of Cauchy-Riemann equations is in the paper I wrote with Min and Spencer and Beilu in the end of 2012. It got published mid-13. Where did the thing go? Curses. I'll post this once we actually have a place to post stuff. I will post this. This also has like a bunch of, I gotta warn you. No left. If you look at this paper, my usage of the term left linear versus right linear map is flipped over, unfortunately. As I mentioned this to you guys who were here last time, but anyway, getting to the point. Here's some Cauchy-Riemann equations, like this one. So if it's complex differentiable, that means that the Jacobian matrix ux, uy, man, it's super tiny. I hate these wide margins, they're obnoxious. So ux, vx, uy, vy, that's the Jacobian matrix we talked about in advanced calculus, you guys know. If it has to match that pattern, that means that we have to have ux is equal to vy, and of course, minus vx is equal to uy. Those are the standard Cauchy-Riemann equations we learn in the complex variables course. For the hyperbolic numbers, we have to have that pattern, a, b, b, which means that, again, ux is equal to vy, but in this case, vx is equal to uy, no minus. And then there's like Cauchy-Riemann equations for the null numbers, look like this. Ux is equal to vy, uy is just equal to 0, and vx is free. So that's kind of weird. And anyway, if you look at this, here's the Cauchy-Riemann equations for the 3 hyperbolic numbers. We have to match the Jacobian matrix to the shape of the regular representation. So that gives me the equality of this from the diagonal, and then the W's have to match for the, that's essentially the B term, and the C term, so to speak, is this and that have to match. So if you look at it, there's 1, 2, 3, 4, 5, 6 Cauchy-Riemann equations for the 3 hyperbolic numbers. If you do the counting, it makes sense. So the regular representation is 3-dimensionals for H3. And to say that the Jacobian matrix is in the regular representation is to say it's in the subalgebra of, the 3x3 matrices, which corresponds to the 3 hyperbolic numbers. So if you want to define a space by equations, it's codimension, right? I need 6 equations in a 9-dimensional space to pick out a 3-dimensional subspace. So there has to be 6 Cauchy-Riemann equations to pick out a 3-dimensional subset of 3x3 matrices. So for a 4-dimensional algebra, you get 16 minus 4. You get 12 Cauchy-Riemann equations. For a 5-dimensional algebra, you get 20 Cauchy-Riemann equations. For a 6-dimensional algebra, you get 36 minus 6. You get 30, and you see how it goes. So the fact that there's just 2 Cauchy-Riemann equations is very, very special to complex analysis. There's usually a lot more. Oh, here's Spencer's A Laplacian. I haven't looked at it much lately, but we figured out that all of the components of an A differentiable function have to satisfy this equation. For example, the A Laplacian for the complex numbers is just the ordinary Laplacian. The Laplacian for the hyperbolic, A Laplacian for the hyperbolic numbers is just the basically the operator, which gives you the wave equation. The A Laplacian for the null numbers is just partial x squared. Weird. The A Laplacian for the 3 hyperbolic numbers is this guy. You recognize these patterns. Essentially, I'm just taking the determinant zero divisor formula and replacing the ABC with corresponding partial derivatives. But this came before that, okay? Or kind of the same time. This is Spencer's invention. And, anyway, we were able to prove that if you had a commutative semi-simple algebra, then the component functions of an A differentiable function automatically solve the A Laplacian. In the sense that if you take the A Laplacian and act on them, it gives you 0. I have a slightly deeper understanding of it now than when we wrote the paper, though. So, but anyway, it's not really where I'm at the moment. At the moment, I'm really just trying to understand calculus deeply over an algebra, and so we'll get back to that next time. So my goal next time is just to describe how we define a differentiability and how we, what the major results we have on it, and then we'll go from there. Hopefully, I'll hopefully get to integration by. Well, then again, Cooper, it would be helpful to you if I kind of go sideways and talk about the conformal, because we can talk about that earlier. Once we just need to talk about a differentiability a little bit. That will get us to the chain rule, and then we can start thinking about the conformal mapping stuff. We can do that next week, actually. So I will be aiming to get to the hyperbolic conformal mapping before. That's not in this paper. My paper isn't, but anyway, sorry if this is vague so far. We will discover things for you guys to do as it goes on. So whenever I find a problem in here, what you should do is try to write it out and maybe type it up and just make a try to collect a ongoing list of things we've done, maybe put a date on it so we can figure out where we did it, and I'll keep posting these and so forth. Okay, thanks guys. I will shut up. So we are not meeting tomorrow, to be clear. What's that? Oh, yes, we need to.